Pick up whatever is closest to you, a phone, a glass, the edge of the blanket, and ask what it is made of. Molecules, then atoms, then a nucleus, and protons, and inside those, quarks. Every step down is smaller and simpler than the one above it, and every generation of physicists has assumed the same thing about that staircase, that it ends. That somewhere down there is a final step, one equation, the bottom of everything. Albert Einstein spent his last 30 years reaching for it, and died with the pages still on the table beside him. Two of the founders of quantum mechanics chased it into their final decades. Thousands of people have sat under a mountain, watching 50,000 tons of water for 40 years, waiting for it to show itself, and nothing has ever happened. And in 108 years of looking, nobody has ever demonstrated that the staircase has a bottom at all. By the end of tonight, you will know exactly why this one idea has ruined more careers than anything else in science, and whether the thing they were all reaching for is even there. Before we begin, if you enjoy questioning something this basic, this slowly, a quick like or subscribe really helps the channel grow. It's a small thing for you, and it means a great deal to me. Now, let's ease in. There were pages on the table when he died. On the 18th of April, 1955, in a hospital in Princeton, New Jersey, Albert Einstein died of an abdominal aortic aneurysm at the age of 76. He had refused surgery. He said he wanted to go elegantly, and that it was tasteless to prolong life artificially, and that he had done his share. And then, in the days he had left, he asked for his glasses, his notes, and a pencil, and he went back to work. What he was working on was not relativity. That had been finished for 40 years. He was working on a unified field theory, and he had been working on it, without a break, since the middle of the 1920s. The pages beside his bed were covered in the same class of equations he had been rewriting for 3 decades. They were an attempt to show that gravity and electromagnetism were not two things but one thing, seen from two angles, and that if you found the right mathematical object, you could write the whole of physical reality in a single expression with nothing left over. He did not find it. The pages went nowhere. They are catalogued now, and you can read them, and no working physicist has ever built anything on them. 30 years, from a mind that had already changed our understanding of space, time, light, gravity, and the atom, and at the end of it, there was a stack of paper that the field politely set aside. I want you to sit with how strange that is, because it is easy to hear it as a sad story about an old man and miss what it actually is. Einstein was not confused in those years. He was not ill until the very end. He was working with total seriousness on the problem he considered the most important in physics, in the best resourced institution in the world, with unlimited access to anyone he wanted to talk to, and the work produced nothing. The thing he was chasing has a lot of names. Physicists have called it the unified field theory, and the world formula, and the final theory, and the theory of everything. Outside the field, it usually gets called the Holy Grail of physics. And that phrase, which sounds like a piece of journalism, turns out to be uncomfortably precise. A grail is an object of a specific kind. It is defined by being sought. Its value is in the seeking. And in the oldest versions of the story, the knights who go looking for it do not come back. Here is what I would like you to notice tonight, because it is the thing that made me want to tell you this story in the first place. Einstein is not the exception in this history. He is somewhere in the middle of a list. Before him, there was Hermann Weyl, who in 1918 proposed the first modern unification of gravity and electromagnetism, and who withdrew it after Einstein himself pointed out that if the theory were true, atoms could not stay the same size. There was Theodore Kaluza, who in 1919 worked out that if you write general relativity in 5 dimensions instead of 4, electromagnetism falls out of the extra one for free, and who then spent roughly 20 years as an unsalaried lecturer while the world got around to noticing. There was Arthur Eddington, who was in the 1920s one of the most celebrated scientists in Britain, and who spent the last 15 years of his life trying to derive the constants of nature out of pure number, and who died with the manuscript unfinished, and whose reputation has never fully recovered. There was Erwin Schrödinger, who in January of 1947 called a press conference in Dublin to announce that he had solved it, with the head of the Irish government sitting in the audience, and who watched the whole thing come apart within a matter of weeks. There was Werner Heisenberg, who in 1958 went on the radio to describe a world formula as essentially finished, and whose own collaborator responded by mailing their friends a drawing of an empty rectangle. And after all of them, when the mathematics had improved beyond recognition and the instruments had become the largest machines ever built, it kept happening. A generation of physicists built careers on a theory that predicted the proton would fall apart, and then sat in mines under mountains for 40 years watching tanks of water in which nothing ever fell apart. Another generation built careers on a family of particles that the next collider was certain to reveal, and the collider was cancelled in October of 1993 with 14 miles of tunnel already bored under Texas farmland, and $2 billion already spent. And when a different collider was finally built, the particles were not there either. And a third generation, thousands strong, has now spent 40 years on a framework so flexible that it can describe something on the order of 10 to the 500 different universes, exactly one of which is ours, with nothing in the theory to tell you which. That is 108 years of continuous, sophisticated, well-funded failure carried out by people who were, in many cases, the most capable scientists alive. Now, science is full of hard problems, and hard problems take a long time, and there is nothing remarkable about a question staying open for a century. What is remarkable about this one is the wreckage. Most difficult problems in science are generous to the people who work on them. You attack the problem, you fail to solve it, but you produce a piece of the answer along the way, and that piece is publishable and citable, and it becomes the foundation somebody else builds on, and your career is made out of the fragments. Fermat's last theorem stayed open for 358 years, and the attempts to crack it built entire branches of modern number theory, and the mathematicians who failed at it are remembered warmly for what they made on the way. The final theory does not work like that. It is defined by totality. A framework either unifies everything or it unifies nothing, and there is no partial version that counts as an answer. Worse, the energies at which the answer would show itself are around 10 to the 19th giga-electron-volts, and the most powerful machine humanity has ever built reaches about 10 to the 4th. That is a gap of 15 orders of magnitude, so there is no partial credit, and there is also no way to check your work. You can spend 30 years producing mathematics of genuine beauty and finish with nothing that anyone can weigh, confirm, deny, or build on. That combination, no partial credit and no test, is what makes this particular ambition so expensive in human terms. It will accept any amount of talent you feed into it and give back no signal at all about whether you are getting closer. And so I want to walk you through it slowly tonight, name by name, decade by decade, because when you lay them out in order, something starts to show through the individual stories that none of them could see from the inside. These people used completely different mathematics. Weyl used differential geometry. Kaluza used extra dimensions. Eddington used number theory. Heisenberg used nonlinear field equations. The modern attempts use group theory and two-dimensional conformal field theory and objects that do not have a name in ordinary language. There is almost nothing technical that connects them. They failed in exactly the same way. When 100 years of unrelated methods all produce the same outcome, there are two things that could be going on. The first is that the problem is simply very hard, and we are in the middle of a long climb, and everyone on this list is a stone in a road that eventually arrives somewhere. That is the comfortable reading, and a great many serious physicists hold it. The second possibility is the one that makes people uncomfortable, and it is the question I am going to hold open for the next couple of hours, rather than answer now. Every single person in this story began from an assumption they never examined, because it did not look like an assumption. They assumed the thing was there. They assumed that underneath the layers of physics there is a bottom, a final layer, one equation, and that the universe is shaped like a pyramid, narrowing to a point. Nobody has ever demonstrated that. It is an inheritance, and I will show you exactly where it came from. And it came from a single spectacular success in the 1860s that everyone since has been trying to repeat. So by the end of tonight, you will know why this idea has ruined more careers than any other in science. But the question underneath it, the one I want you carrying through all of this, through Kaluza's 20 years, and Eddington's number, and the empty tank under the mountain, is simpler and much harder. Is the Grail actually there? I am not going to tell you yet. Let me take you back to the one time it worked. Before it started killing careers, it worked exactly once, and it worked so beautifully that physics has never recovered. In the middle of the 19th century, electricity and magnetism were two separate subjects. They were known to interfere with each other in odd ways. Michael Faraday, working in the basement of the Royal Institution in London, had spent decades documenting those interferences with extraordinary care and almost no mathematics, because he had almost no mathematics. He had left school at 13. What he had instead was an unusual physical imagination, and he pictured the space around a magnet as being filled with something, invisible lines of tension running from pole to pole, a condition of the space itself rather than an action passing across empty distance. Other physicists found this vague. It was, as it turned out, the single most important idea of the century. James Clerk Maxwell was a Scottish mathematical physicist who took Faraday's picture seriously enough to write it down properly. Over a series of papers culminating in 1865, in a paper called A Dynamical Theory of the Electromagnetic Field, he produced a set of equations describing electric and magnetic fields as two aspects of a single object. A changing electric field produces a magnetic one. A changing magnetic field produces an electric one. And once you have written that down honestly, you notice something you did not put in on purpose. The equations permit a wave. An electric field changes, which produces a magnetic field, which changes, which produces an electric field, and the disturbance walks itself forward through empty space, with nothing carrying it but its own two halves taking turns. Waves have speeds, and the speed of this one was not a free choice. It was fixed by two numbers that describe how strongly empty space responds to electricity and to magnetism, and both of those numbers could be measured on a laboratory bench with equipment that had nothing whatsoever to do with light. Wilhelm Weber and Rudolf Kohlrausch had already made the relevant measurement in 1856, using capacitors and currents. Maxwell put their numbers into his expression and turned the handle. The answer came out at roughly 310,000 kilometers per second. The best measured value for the speed of light at the time, from Hippolyte Fizeau's work with a rotating toothed wheel and a mirror across Paris, was around 315,000 kilometers per second. The modern figure is 299,792.458 kilometers per second. Maxwell's calculation and the measured speed of light agreed to within a few percent, which in 1865, with those instruments, is agreement. He wrote that the velocity was so nearly that of light that it seemed there was strong reason to conclude that light itself is an electromagnetic disturbance, propagated through the field according to electromagnetic laws. Take a moment with that sentence, because it is one of the great moments in the history of thought. A man doing bookkeeping on magnets and wires had accidentally derived light, not described it, derived it. Optics, a subject that had been studied independently for 2,000 years, with its own instruments, its own vocabulary, its own community, turned out to be a sub-discipline of electricity. Two enormous regions of human knowledge that had grown up separately were revealed to be one region with a wall painted down the middle of it. And then it did the thing that separates a real unification from a pretty rearrangement. It made a prediction about something nobody had ever seen. If light is an electromagnetic wave, the wavelength is not fixed by anything. You should be able to make these waves at any wavelength you like, including wavelengths thousands of times longer than visible light, which would be entirely invisible and would pass through walls. Nobody had ever observed such a thing. Maxwell died in 1879 at the age of 48 without seeing one. In 1887, in Karlsruhe, Heinrich Hertz built a spark gap and a wire loop across the room and detected the invisible waves passing between them at the speed the equations demanded. He is said to have remarked that the discovery was of no use whatsoever. Every radio, every television broadcast, every mobile phone call, every Wi-Fi router, every radar installation, and every deep space probe transmission in the history of the species is a use of that discovery. The signal that carried this video to you is a Maxwell wave. So the score, at the end of the 19th century, was this. A single act of unification had merged two entire sciences into one, predicted a phenomenon nobody had imagined, and handed the 20th century its nervous system. The reward for finding the deeper structure underneath two apparently separate forces was not incremental. It was total. That is the moment the addiction starts. Because once you have seen it happen, once you have watched two forces turn out to be one thing, wearing two costumes, a certain thought becomes almost impossible to resist. If electricity and magnetism were secretly one, why stop there? Gravity is also a field. Gravity also fills space. Gravity also has lines of influence running out from a source and falling off with the square of the distance, exactly the way an electric field does. The mathematical resemblance between Newton's law of gravitation and Coulomb's law of electrostatics is so close that you can turn one into the other by changing the letters. Surely gravity and electromagnetism are also one thing. Surely there is another Maxwell moment waiting, one level down, for whoever gets there first. That thought is the seed of everything that follows in this story, and I want to be very careful about how I describe it, because it is not a stupid thought. It is an extremely good thought. It is the same instinct that produced every major advance in physics for 300 years. The instinct that says apparent variety is hiding real simplicity, that the number of separate things in the world is smaller than it looks, that if you dig, you will find fewer laws rather than more. That instinct has been right many times. It has never been proven to be right always. And here is the detail that should sit slightly uncomfortably as we go forward. Maxwell's unification is one event. 1. In the entire history of physics, there have been exactly two unifications that were proposed, tested, and confirmed. Maxwell's in 1865 and the electroweak unification in the 1960s, which we will come to. Two data points in 350 years are being used as the foundation for the belief that everything unifies. Nobody thought of it that way at the time, and honestly, nobody thinks of it that way now. What everybody thought in the first decades of the 20th century was that a door had been opened and there was obviously another door behind it. So they went looking, and the first man through was not a physicist at all. He was a mathematician. He was one of the finest of his generation, and he got remarkably close to something correct. Close enough that the framework he invented now underpins 3 of the 4 forces of nature. It did him no good at all. Hermann Weyl was not a man you would expect to lose. He was born in 1885 in a small town near Hamburg, studied at Göttingen under David Hilbert, who was, at that point, arguably the most powerful mathematician on Earth, and by his early 30s held a chair at the Federal Institute of Technology in Zurich. He wrote a book on Riemann surfaces that reorganized the subject. He wrote the first serious mathematical exposition of general relativity, published in 1918, which physicists were still learning from decades later. He would go on to do foundational work on the representation theory of groups, which is now one of the load-bearing walls of quantum physics. If you were assembling a list of the people most likely to solve a deep structural problem in mathematical physics in 1918, he would be near the top of it. That same year, he thought he had solved this one. The idea begins with a detail in Einstein's general relativity that almost nobody questions, because it does not look like a choice. In curved spacetime, if you take a vector, an arrow, a direction with a length, and carry it around a closed loop, keeping it as parallel to itself as the curvature allows, it comes back rotated. That rotation is what gravity is. In the geometric picture, it is the whole content of the theory. But the arrow comes back the same length. Its direction has been altered by the journey. Its magnitude has not. Weyl asked a very simple question: why not? If the geometry does not preserve direction, why should we assume it preserves length? What if the standard of length is also local? What if the meaning of 1 meter here and 1 meter over there is set independently, and comparing them requires you to carry a calibration along a path, and the calibration also changes as it goes? He worked out the consequences. When you allow the scale of the geometry to shift from point to point, the mathematics requires an extra field to keep track of how the calibration is being adjusted as you move. That field has to have 4 components, one for each direction in spacetime. It has to obey a particular set of equations. And when Weyl wrote down what those equations were, they were Maxwell's. Gravity was the curvature of the geometry. Electromagnetism was the stretching of the geometry. 1 structure, 2 forces, no seam. He called the freedom to reset the scale at every point eigenvariance, calibration invariance. In English, that became gauge invariance, from the railway sense of gauge, the standard distance between the rails that has to be agreed on for anything to run. He sent the paper to Einstein in the spring of 1918, asking him to submit it to the Prussian Academy. Einstein submitted it. He also attached an objection printed in the same volume immediately after the paper. The objection is one of the most efficient in the history of physics, and it does not involve a single line of difficult mathematics. Einstein pointed out that if the length of a physical object depends on the route it has taken through an electromagnetic field, then 2 identical atoms that have traveled different paths will end up different sizes. And the size of an atom is not a private matter. It determines the frequencies of light that atom emits. 2 hydrogen atoms with different histories would sing at different pitches. Then he pointed at the sky. We can see hydrogen atoms across the observable universe. We have been measuring their spectral lines since the 1860s. A hydrogen atom in a laboratory in Zurich and a hydrogen atom in a galaxy whose light left it billions of years ago produce the same set of lines, in the same places, with a precision that leaves no room whatsoever for the effect Weyl's theory required. Atoms do not remember where they have been. Whatever else is true about the universe, the standard of length is not a local convention. The theory, as a theory of electromagnetism, was dead on arrival. It was killed not by an experiment anyone had to build, but by the fact that stars have been visible for as long as there have been eyes. Weyl fought for it for a while, and then conceded. And here I want to slow down, because what happened afterwards is the reason his name is in this story rather than in a footnote. In 1925 and 1926, quantum mechanics arrived. And in quantum mechanics, A particle is described not by an arrow with a length, but by a wave function. And a wave function has a property that classical objects do not have, a phase. Think of it as the position of a hand going round a clock face. The phase is not directly observable. Only differences in phase between one place and another have any physical meaning at all. Which means the phase is exactly the sort of quantity that could be locally arbitrary. In 1929, Weyl went back to his own idea and changed one thing. Instead of the geometry rescaling the length of a vector as you move it, the transformation rotates the phase of a quantum wave function. Everything else in the structure stays. And when you demand that physics not care about the local setting of that phase, you are forced to introduce a compensating field with 4 components obeying a particular set of equations. They are still Maxwell's. Only now the theory is correct. It is quantum electrodynamics, the most precisely tested theory in the history of science. And that was not the end of it. In 1954, Chen-Ning Yang and Robert Mills took the same principle and applied it to a more complicated internal symmetry than a simple phase rotation. And that generalization is what the weak nuclear force and the strong nuclear force are both built out of. Every force in the standard model of particle physics, electromagnetic, weak, strong, is a gauge theory, and gauge theory is Weyl's 1918 idea, with the physical interpretation corrected. He is one of the most important physicists of the 20th century, and the thing that made him important is a corrected version of a theory he was forced to abandon. There is a small linguistic fossil left behind by all of this that I find quietly haunting. The modern concept has nothing to do with rulers. It concerns the phase of a wave function, an angle on an abstract clock face with no length in it anywhere. And yet the name physics uses for it, every day, in every textbook, and every seminar, and every paper, is still gauge, the railway word, from the discarded version, from the theory about the size of things that turned out to be wrong. The field kept the vocabulary of the failure, and quietly replaced the physics underneath it. There are graduate students today who will use the word 10,000 times in a career without ever learning that it refers to a mistake made in 1918. Weyl himself left Germany in 1933 when the political situation made staying impossible, and took a position at the Institute for Advanced Study in Princeton. So, for the last 20 years of Einstein's life, the man whose unified field theory Einstein had demolished with a single remark about hydrogen was working down the corridor from him, while Einstein worked on a unified field theory of his own that would fare no better. So what actually went wrong in 1918? Not his mathematics. The mathematics was right, and it survived intact, and we still use it. What was wrong was the thing he attached it to. He hung the idea on the length of a ruler, because in 1918, length was the only quantity available to hang it on. The quantity it needed, the phase of a wave function, would not exist as a concept for another 8 years. He built a perfectly sound machine and connected it to the wrong part of the universe, because the right part had not been discovered yet. I want you to keep that in your hands, because we are going to see it again and again tonight, in different clothes. Weyl did not fail because he was not clever enough. He failed because he was working on the final theory before the ingredients of the final theory existed, and there is no way to know from the inside whether that is the situation you are in. There is no alarm that sounds. From where he was standing, in Zurich in 1918, with gravity and electromagnetism dropping out of one geometry, it looked exactly like arriving. That is the first hard thing about the Grail. It does not tell you how far away it is. It cannot, because nobody knows where it is, or whether the direction anyone is walking in is the direction it lies. And the man who came next did not even get the courtesy of a public objection. He got silence, for 2 years, from the only person whose opinion mattered. The next idea was so strange that the man who had it waited more than 2 years for permission to publish, and then waited 20 more for a salary. Theodor Kaluza was a lecturer at the University of Königsberg, in what was then East Prussia. His title was Privatdozent, and it is worth understanding what that meant, because the phrase gets translated as lecturer and sounds ordinary. A Privatdozent had earned the right to teach at a German university. The university did not pay him for it. He was compensated directly out of fees paid by the students who chose to attend his lectures, which meant his income depended on how many people turned up to hear him talk about mathematics. It was understood as a waiting room. You spent 3 or 4 years there, sometimes 5, and then a chair came open somewhere, and you moved into a real position. Kaluza was in that waiting room for about 20 years. In 1919, while he was in it, he had an idea about the structure of reality that nobody had had before. General relativity describes gravity as the geometry of a 4-dimensional space-time, 3 dimensions of space, 1 of time. The mathematical object that carries the geometry is called the metric, and in 4 dimensions, it is a symmetric grid of numbers at every point, 4 across and 4 down, which because of the symmetry has 10 independent entries. Those 10 numbers are gravity. That is the whole theory. Kaluza asked what happens if you write down exactly the same theory in 5 dimensions. Nothing about Einstein's equations forbids it. The mathematics is indifferent to how many dimensions you feed it. In 5 dimensions, the metric becomes 5 across and 5 down, and a symmetric grid that size has 15 independent entries instead of 10. So you get 5 extra numbers at every point in spacetime, and the question is what they do. 4 of them assemble themselves into an object with 1 component for each direction of ordinary spacetime. And when you take the 5-dimensional Einstein equations and separate out the part governing those 4 numbers, they satisfy Maxwell's equations. I want to sit inside that moment with you, because it happened in a small room and nobody else was there. It is spring, in Königsberg, and the light through the window is the flat grey light of the Baltic. There is a desk, and on it a sheet of paper with an object written out that has no business existing. Einstein's field equations, the newest and most celebrated mathematics on Earth, but with a 5th line and a 5th column added for no reason except to see what happens. He works through the decomposition by hand. There is no machine to check it. The 10 familiar entries come out as gravity, exactly as they should, which is reassuring and expected. Then he turns to the leftover 4 and begins reducing them, and what appears under the pencil is a set of equations he has known since he was a student. Equations about coils and currents and light, equations that belong to a completely different branch of physics and have absolutely no reason to be here. Electricity and magnetism have arrived from nowhere, uninvited, as a side effect of adding 1 direction to space. He is 34 years old. He is being paid by the head to teach undergraduates, and he is alone in a room in East Prussia, holding what looks, for a moment, like the structure of the universe. He wrote to Einstein about it in April of 1919. Einstein wrote back on the 21st of that month, and he was delighted. He said the idea of achieving unification by means of a 5-dimensional cylinder world had never occurred to him, and that at first glance he liked the idea enormously. Then nothing happened for 2 years. Einstein was the gatekeeper. To appear in the proceedings of the Prussian Academy, the paper needed a member to submit it, and Einstein was the member. He raised objections, then withdrew them, then raised others. He was working on his own approaches at the time. The paper was finally communicated to the Academy and published in 1921, more than 2 years after it had been written. The obvious problem with a 5th dimension is that nobody has ever been in one. Kaluza handled this by imposing what he called the cylinder condition. He simply required that nothing in physics depends on position along the 5th direction. It is a legitimate mathematical move, and it makes the theory work. And it is also an announcement that you do not know why the extra dimension is hiding. The answer came from Oskar Klein, a Swedish physicist, in 1926. Klein proposed that the fifth dimension is not infinite like the others, but closed into a circle, and that the circle is extremely small. His estimate put the radius at something around 10 to the minus 30 meters, which is roughly 20 orders of magnitude below the width of a proton. You cannot travel along it, because if you set off, you arrive back where you started, before you have gone anywhere at all. At every point of the space you are sitting in right now, there would be a loop, and the loop would be so small that no experiment ever performed could resolve it. And Klein's version gave something back. If the extra dimension is a closed loop, then a quantum wave living on it has to fit a whole number of wavelengths around the circle, the way a guitar string can only vibrate in whole numbers of half waves. Those whole numbers turn out to correspond to units of electric charge, which would explain something nobody has ever explained: why electric charge comes in exact multiples of a single unit, and never in fractions of it. Charge is quantized because the hidden dimension is a circle. That is a genuinely beautiful piece of physics, and by the end of the 1920s, it was more or less abandoned. Part of the reason was technical. The 15th number, the leftover scalar field describing the size of the little circle, did not behave. Nothing in the theory held the circle at a fixed radius, and a circle free to change size produces effects on gravity that are not observed. Part of the reason was timing. 1926 was the year quantum mechanics arrived in force, and every capable young theorist in Europe ran toward it. A speculative five-dimensional geometry could not compete with an explosion. Kaluza stayed in the waiting room. He was still a privat docent at Königsberg at the end of the 1920s, roughly 2 decades after qualifying, and it was only in 1929, reportedly after Einstein wrote in support of him, that he received a professorship at Kiel. He was 44. He worked in relative obscurity for the rest of his career and died in 1954. There is a story told about him that has become the thing he is remembered for, and it is almost too neat. As an adult, Kaluza could not swim. He read a book about swimming, studied it thoroughly, went to the water, and swam. He trusted a theory enough to put his body in it. 60 years after his paper, string theory arrived, and it requires 10 dimensions, 6 of which have to be hidden. The mechanism it uses to hide them is Klein's, small compact geometries at every point of space, with the shape of the hidden part determining what particles you see. The entire modern hope of unifying gravity with the other forces sits on top of Kaluza's 5-dimensional guess and Klein's curled circle. It is one of the most influential ideas of the 20th century. He got 2 years of silence, 20 years of student fees, and a professorship at 44. And I want to point at something quietly, because it will matter later. Kaluza's idea did not fail. That is the odd thing. It was absorbed. The same is true of Wales. The Grail hunt keeps producing mathematics that turns out to be indispensable, while never producing the thing it set out to find, which is a strange kind of failure, as if the search were reliably useful and reliably wrong at the same time. Einstein watched both of these men closely. He read Weyl's paper and destroyed it. He read Kaluza's paper and sat on it. And then he spent the last 30 years of his life doing exactly what they had done, in a room with better furniture and considerably more people watching. By 1925, Albert Einstein had nothing left to prove to anyone, which is precisely when the trouble started. Consider where he was standing. He had explained the photoelectric effect in 1905 and would receive the Nobel Prize for it. He had explained Brownian motion in the same year, and in doing so, settled the question of whether atoms existed. He had written special relativity that year as well, and then, over the following decade, general relativity, which replaced Newton's picture of gravity with the geometry of spacetime and predicted that starlight would bend as it passed the sun. In 1919, that prediction was confirmed during a solar eclipse, and he became, essentially overnight, the most famous scientist who has ever lived. He was 46 years old. And then quantum mechanics arrived, and he did not accept it. This is the hinge of the whole story, so let me be careful about what actually happened, because the popular version is wrong. Einstein did not fail to understand quantum mechanics. He had helped build it. The photoelectric paper is a quantum paper, and he did foundational work on stimulated emission that made the laser possible. He understood it thoroughly. What he refused was the claim that it was finished. He thought a theory that could only give you probabilities for what a particle would do, rather than an account of what the particle actually is and is actually doing, had to be an approximation to something deeper. In a letter to Max Born in 1926, he wrote the line, "Everyone knows about the old one not playing dice." In 1935, with Boris Podolsky and Nathan Rosen, he published the paper arguing that quantum mechanics cannot be a complete description of physical reality. Now, hold two facts together. First, Einstein believed the quantum theory was provisional. Second, he intended to find the theory underneath everything. Put those together, and you get the decision that shaped the last 3 decades of his life. He built his unified field theories out of classical continuous fields, smooth, deterministic, geometric objects of the kind general relativity is made from, and deliberately did not use the mathematics that the rest of physics had just adopted. He was going to unify physics using a toolkit the field had left behind, on the grounds that the field had left it behind too soon. What followed was 30 years of sustained, serious, published effort in one framework after another. In the late 1920s, he worked on distant parallelism, sometimes called teleparallelism, in which spacetime carries not only curvature, but a way of comparing directions at separated points, and the extra structure was meant to give you electromagnetism. In the 1930s, he returned to 5-dimensional approaches related to Kalusas, working with Peter Bergman and Valentine Bargmann. He tried theories built on bivectors. From the mid-1940s until his death, he worked on non-symmetric field theories, in which the metric, the object describing the geometry, is allowed an antisymmetric part, and that part is identified with the electromagnetic field. The 1953 edition of his book, The Meaning of Relativity, carries an appendix setting this out. He revised the appendix again for the 1955 edition, which appeared the year he died. The 1929 version produced one of the strangest scenes in the history of scientific publishing. Einstein published a short paper on distant parallelism, and because it was Einstein, and because the words unified field theory were attached to it, the world's press treated it as an event. Newspapers printed the field equations themselves, as though readers might check them. It is reported that a London department store put the pages of the paper up in its display window, and that crowds gathered on the pavement to look at them. People queued to see mathematics they could not read, on the assumption that the universe had just been explained. Within about 2 years, Einstein had abandoned that approach entirely. And here is the part that is easy to miss when the story is told as a tragedy of an old man being stubborn about dice. The deeper problem was not philosophical. It was that he was trying to unify the wrong number of forces. When Einstein began, in the mid-1920s, physics knew of 2 forces, gravity and electromagnetism. Unifying 2 things is a well-posed problem. But during the 1930s, physics discovered that the nucleus is held together by something new, the strong force, and that radioactive decay is governed by something else new again, the weak force. By the middle of his effort, the count had gone from 2 to 4, and the 2 new ones are inherently quantum, short range, and have no classical geometric description of the kind he was working in. There is no version of a smooth, continuous field theory that produces beta decay. So the target moved, and it moved in a direction that made his chosen tools useless, and he kept going. Let me put you in the room, near the end. It is a weekday morning in 1954 at the Institute for Advanced Study in Princeton, and the most famous scientist on Earth is at his blackboard. He is 75. The office is not grand. There is a board and chalk and the particular smell of a room where someone smokes a pipe and thinks. On the board are equations that a physicist from any other office in the building could read the shape of without being able to say what they are for. A metric with an antisymmetric part, the same class of object he was manipulating in 1945 and in 1938, and in a recognizable ancestral form in 1928. He works through a variation and looks at what it gives, and it does not give electromagnetism, and he erases it. Down the corridor there are people doing quantum electrodynamics, which in the previous 6 years has produced predictions matching experiment to better than 1 part in a billion. Nobody down that corridor is working on what he is working on. They are courteous about it. Some of them are protective of him. Almost none of them ask, any more, what is on the board. He puts the chalk down and picks it up again and starts the next variation. There is no result today. There was no result yesterday. He is entirely aware of this, and he will be back tomorrow. He knew exactly how he appeared. In an autobiographical piece, written around 1949, he described himself as being regarded by his colleagues as a kind of petrified object, someone rendered blind and deaf by the passing years. That is not self-pity. It is an accurate report, written by a man with excellent hearing. Robert Oppenheimer, who directed the Institute during Einstein's final years there, and who admired him personally, later described his late work in terms that amounted to a courteous burial, the sense being that Einstein had spent his last decades in a cul-de-sac of his own choosing, and that the effort had been fruitless. That was the general view. It is still the general view. There is a detail here that rarely gets mentioned, and it belongs in a story about ruined careers more than anything else in this part. Einstein did not work entirely alone. He had assistants, young physicists, often very good ones, who came to Princeton to work with the most famous scientist in the world, and who therefore worked on unified field theory, because that was what he was doing. Peter Bergman, Valentine Bargmann, Leopold Infeld, Ernst Strauss, Breuer Kaufmann. They spent years of their early careers inside the project. For some of them it worked out. Bergman became a founder of the field of canonical quantum gravity and trained a generation. But think about the position they were in at the time. You are 28 years old, you are extraordinarily talented, and you are spending the most productive years a theorist has computing variations of a non-symmetric metric for a man whose entire approach the rest of your field has already written off. The work will not be cited. It will not lead anywhere, and you cannot say so because you are in the room with Albert Einstein and he believes in it. The Grail does not only consume the person chasing it, it quietly draws in everyone standing near them, and their names are much easier to forget. So why did he keep going? Because he thought somebody had to. He said, more than once and in various forms, that he was working alone, that his colleagues did not follow him, and that this did not change what he believed the problem to be. He held that the statistical description could not be the final word about a stone falling or a star burning, and that if everyone chased the successful theory, nobody would be standing where the unsuccessful question was. There is a version of that which is admirable, and a version which is a man declining to update, and the honest answer is that from inside a single life you cannot tell which one you are living. On the 18th of April, 1955, the aneurysm in his abdominal aorta ruptured. He had known about it for years and had declined surgery. In Princeton Hospital, in the last day or so, he asked for his most recent pages so he could continue. Those are the pages I opened with. This is what was on them. Not a triumph, interrupted by death. The 300th attempt at the same maneuver, in a framework that could not accommodate two of the four forces, by a man who had known for 2 decades that his colleagues considered the entire project a private hobby. And I want to be very clear about the thing I am not saying. I am not saying he wasted his life. He gave us the 20th century before he was 40. What I am saying is narrower and stranger. The single greatest physical intuition of the modern era, given 30 uninterrupted years, unlimited resources, and complete freedom, aimed directly at the holy grail of physics, produced nothing that anyone has been able to use. If it did not work for him, the question of whether it can work at all becomes a real question rather than a rhetorical one. There is one more thing about those 30 years worth holding on to. He was not deluded about his progress. He wrote to friends about how difficult it was and how little he had. What he was certain of was not that he was close. What he was certain of was that the thing was there to be found. That certainty was inherited, not derived, and it was about to do something to a very fine mind that is harder to watch than anything Einstein went through, because Einstein, at least, never fixed his results to match the answer. Arthur Stanley Eddington is the reason you have heard of Albert Einstein. In 1919, Eddington led an expedition to the island of Principe, off the west coast of Africa, to photograph a total solar eclipse. The point was to measure whether starlight passing close to the sun is deflected by the sun's gravity, and if so, by how much. Newton's physics allowed a small deflection. General relativity predicted twice as much, about 1.75 arcseconds at the solar limb. The plates came back. The measurement favoured Einstein, and the announcement in London in November of that year turned a German physicist into a global celebrity, 14 months after the end of a war in which Britain and Germany had spent 4 years killing each other. Eddington was a Quaker and had been a conscientious objector, and the international character of the result was, for him, part of the point. He was also the leading astrophysicist of his generation, by a comfortable margin. His book, The Internal Constitution of the Stars, published in 1926, worked out how stars hold themselves up and established that the energy source had to be subatomic at a time when nobody knew how nuclear fusion worked. He wrote popular books that sold enormously. He was knighted. There is a much-repeated story that a journalist told him he must be one of only 3 people in the world who understood general relativity, and that Eddington paused and said he was trying to think who the third one was. That is the man who, from about 1929, walked into the Grail and did not come out. His project was more radical than anything we have looked at so far. Weyl, Kaluza, and Einstein were all trying to unify forces. Eddington wanted to derive the constants of nature, the raw numbers of the universe, from pure reasoning. Not measure them, deduce them, the way you deduce that a triangle's angles sum to a straight line, from the structure of the situation, with no experiment required. The centerpiece was a number called the fine structure constant. It is worth a moment, because it is one of the genuinely eerie objects in physics. Most constants have units attached. The speed of light is so many meters per second, and its numerical value depends on whether you chose meters or feet. The fine structure constant has no units at all. It is a pure number, roughly 1/137, and it measures how strongly light and matter interact, how firmly electrons are held to nuclei, and therefore what chemistry is possible, and therefore whether there can be anything complicated in the universe. Any civilization anywhere, using any units, measuring anything, gets the same number. Richard Feynman called it one of the greatest mysteries in physics, and said all good theoretical physicists put it on their wall and worry about it. Wolfgang Pauli was preoccupied with it his entire life, and, this is true, and slightly too neat, died in room 137 of a Zurich hospital. And the reason it obsesses people is that it appears to be load-bearing. The strength of the electromagnetic interaction sets the size of atoms, the spacing of energy levels, the rates of the nuclear reactions inside stars. Change that number by a few percent in either direction, and the delicate resonance that lets stars manufacture carbon starts to fail, and a universe without carbon is a universe without chemistry of the interesting kind. So here is a pure number, with no units, that no theory predicts, that we can only measure, and on whose precise value the existence of complicated things appears to depend. You can see why a certain kind of mind looks at that and refuses to accept that it is simply a brute fact we happen to find lying there. Eddington decided this number was not a measurement. It was a count. He constructed an argument based on the number of independent components in a particular mathematical object describing an electron pair, 16 by 16, giving 256 entries, from which a symmetry argument removes some and returns others, and arrived at exactly 136. Not approximately, exactly. The inverse fine structure constant, he announced, has to be 136, because the universe cannot count any other way. Then the experimentalists improved their measurements, and the value moved. It was looking less like 136 and more like 137. And Eddington went back into the derivation and rebuilt it, and it produced 137. I would like to stop here, because this is the moment I find hardest to look at in the entire history, and it is not because it is dramatic. It is because it is ordinary. Consider what has to happen inside a person for this to occur. He is a scientist of the first rank. He has spent years constructing an argument he believes derives a fundamental feature of reality from necessity alone. Then the world produces a number that does not match, and instead of concluding that his argument is wrong, he adjusts the argument until it agrees. This is not fraud. He is not hiding anything. He publishes the revision. He almost certainly experienced it as finding a subtlety he had previously overlooked. That is exactly how it would feel from the inside, but a derivation from first principles that can be rebuilt to land on whatever number the experimentalists last reported is not a derivation at all. It is a very sophisticated way of writing down what you already know. And the man doing it could not see that, because he had already given the project a decade, and the cost of it being wrong had become too large to price. That is what the Grail does to a mind. It does not make you stupid. It slowly moves the place where you allow yourself to stop. His colleagues noticed. The revision from 136 to 137 became a standing joke in physics, and a teasing nickname built on the act of adding one followed him for the rest of his life. The work began to be described as numerology rather than physics, an accusation about method, not about arithmetic. He also produced a derivation of the total number of protons in the observable universe, the so-called Eddington number, arriving at a specific figure of about 1.57 times 10 to the 79th, obtained by multiplying his constant by a large power of 2. Nobody has ever independently reproduced the reasoning. There is a shadow to this that deserves a mention, because it is the same trait doing damage in another direction. In 1935, at a meeting of the Royal Astronomical Society, a young Indian physicist named Subrahmanyan Chandrasekhar presented a calculation showing that a white dwarf star above a certain mass cannot support itself and must collapse. Eddington stood up immediately afterwards and ridiculed it, and his authority was such that the result was widely set aside for years. Chandrasekhar was correct. He won the Nobel Prize for it in 1983. The mass limit is named after him. The certainty that let Eddington rebuild his own derivation is the same certainty that let him crush a correct one belonging to someone else. He worked on fundamental theory until he died, in November of 1944, at 61. The manuscript was unfinished. It was edited and published posthumously in 1946 under that title. It is a dense, difficult, deeply strange book, and it has had essentially no influence on physics. It is read today by historians rather than physicists. The modern measured value of the inverse fine structure constant is approximately 137.03599, known to better than a part in a billion. It is not an integer. It was never going to be an integer. The entire 15-year project was built on the assumption that the universe's most mysterious number would turn out to be a whole one, and that assumption was never tested. It was adopted because whole numbers are what a derivation from counting would produce, and derivation from counting was the goal. The goal chose the assumption. The assumption chose the answer. The answer got adjusted whenever reality disagreed. And notice how different this failure is from the ones before it. Whale was too early. Kaluza was too early. Einstein was using tools that could not reach two of the four forces. Those are failures of timing and of technique. Eddington's is a failure of epistemology. The Grail did not defeat him with mathematics. It defeated him by changing what he was willing to accept as an answer, which raises an unpleasant possibility that we will have to face later. If the target is unreachable, then everyone aimed at it will drift, eventually, towards standards of evidence that let them feel they are making progress. Not because they are dishonest, because there is no other way to keep going. Eddington drifted quietly, in Cambridge, over 15 years. The next man did it in one evening, in front of a head of state and the international press. On the 27th of January 1947, one of the founders of quantum mechanics stood up in Dublin and announced that he had finished the work Einstein could not. Erwin Schrödinger did not need to do this. In 1926, he had written down the wave equation that bears his name, the equation that turned quantum theory from a set of rules into a piece of physics you could calculate with, and which is still the first thing a student meets in a quantum mechanics course. He shared the 1933 Nobel Prize with Paul Dirac. In 1935, in correspondence with Einstein, he produced the thought experiment about a cat in a box that became the most famous image in 20th century science. His position in physics was permanent. How he came to be in Ireland is its own small tragedy. He left Germany in 1933, in disgust at what was happening, and went to Oxford. He then made the extraordinary decision to return to Austria in 1936, to Graz. 2 years later, Germany annexed Austria. Schrödinger, having publicly left over the politics, was now inside them, and he wrote a letter of accommodation to the new authorities, which was published and which he regretted for the rest of his life. It did not save him. He was dismissed anyway, and had to leave the country with, essentially, what he could carry. The man who rescued him was Eamon de Valera, the head of the Irish government, who had trained as a mathematician and taught the subject before politics took him. De Valera created the Dublin Institute for Advanced Studies in 1940 and installed Schrödinger in it. It was an act of considerable personal conviction, and Schrödinger knew exactly whose generosity he was living on. So by the mid-1940s, you have a 59-year-old Nobel laureate in a small institute created for him by a patron who had staked national prestige on the decision, in a neutral country on the edge of Europe, cut off from the centers where physics was moving fast. And he was working on unified field theory. His approach was called affine field theory, and it is worth noticing where it came from, because the threads of this story are tangled together more tightly than they look. The affine approach, building the geometry out of the rule for parallel transport rather than out of a distance measure, had been developed in the 1920s by Eddington and then taken up by Einstein. Schrödinger was working the same seam as the two men we have just watched fail in it, using tools invented by one of them. In January of 1947, he became convinced he had it. Picture the room. It is the Royal Irish Academy, on Dawson Street, in a January that is dark by 4 in the afternoon. The lecture is scheduled, and the audience is not just physicists. Shimon de Valera has come in person, which means the press has come too, which means the room contains people who cannot evaluate a field equation and are here because a great man is going to say something. Schrödinger stands up and presents a generalization of gravitation, which, he says, unifies the gravitational and electromagnetic fields in a single geometric structure. He is careful, in the way of a man who knows the size of the claim, and he is also not careful at all, because he then adds, by the account that was reported at the time, that he believes he is right, and that he will look an awful fool if he is wrong. There is applause. Afterwards he holds a press conference. Reporters who have spent the war writing about rationing write down the words unified field theory and go back to their desks and do their best. The next morning the Irish papers ran it, and the headline that survives from that day, the one that gets quoted whenever the episode is described, announced that a scientist at the Irish Institute had succeeded where Einstein had failed. The story went international within days. It fell apart within weeks. The theory, examined by people equipped to examine it, turned out to be a variant of the same family of geometric constructions Einstein had been working through for 2 decades, with no new physical content, no mechanism connecting it to the quantum world, and, the decisive point, no prediction. It did not say that anything would be observed which had not already been observed. It rearranged the mathematics of gravity into a form that had extra components in it, and asserted that those components were electromagnetism, which is exactly the assertion Weil had made in 1918, and Kaluza in 1919, and Einstein was making at that moment in Princeton. Schrödinger himself came to describe it as preliminary. He kept working in the area for years, publishing quietly and without further announcements, and nothing came of it. Einstein's reaction was cold. The two of them had been corresponding warmly for more than 20 years. It was Schrödinger's letters to Einstein and back that produced the cat, and Einstein regarded the public claim as unserious, both because he thought the theory was empty and because he had spent his life being extremely careful about what he said out loud regarding this exact subject. He criticized it as preliminary, in a way that was not private. The friendship cooled and did not really return. Now, Schrödinger's reputation as a physicist was too large to be undone by this. He is not remembered as a crank. But the Dublin episode is the single thing about his later life that is still told, 40 years after his death, and what it damaged was not his mathematics, it was his judgment, the willingness to convert an unfinished calculation into a public claim in front of a head of state about the most watched unsolved problem in the world. There is a detail about his Dublin years that makes the whole thing considerably sadder. In February of 1943, 4 years before the announcement, Schrödinger gave a series of public lectures in Dublin under the title "What is Life?" In them he asked how a living organism stores the instructions for building itself, and argued that the information must be carried in some kind of aperiodic crystal, a molecule whose structure is not a repeating pattern, because a repeating pattern cannot encode anything. The lectures were published as a short book in 1944. Both James Watson and Francis Crick later said that reading it was part of what turned them toward the problem of the gene. So the most consequential thing Erwin Schrödinger did in Ireland was already behind him when he stood up at the academy. He had, in that small institute, helped launch molecular biology almost as an aside. And then he called a press conference about a set of field equations that went nowhere. He was looking for the Grail, and he walked straight past something enormous on the way to it, and never seems to have noticed which was which. The question worth asking is why a man that capable did something that reckless, and I do not think the answer is vanity. I think there were 3 things pressing on him at once, and any 2 of them would have been enough. The first is that he owed somebody. De Valera had built an institute around him. Schrödinger had been in Dublin for 7 years by then, producing good work, but not spectacular work, and here was a chance to hand his patron something enormous. The second is that he was 59, and he had done the thing he was going to be remembered for at 38, and he knew it. The wave equation was 21 years behind him. That gap is a particular kind of pressure, and it does not get less with time. And the third is the property of this problem that I keep coming back to, because it is the thing that connects every person in this story. There is no test. When you finish a piece of ordinary physics, you can check it. You calculate a number, you compare it with a measurement, and the universe tells you whether you were right. When you finish a unified field theory of this kind, there is nothing to check against. The only available criterion is whether the mathematics feels like it has closed. And a feeling of closure, in a mind that has been working alone on a beautiful structure for 2 years, is not evidence. It is a mood. Every other person in this story had that mood at some point and kept it in a drawer. Weil sent his to Einstein privately and was corrected. Einstein published his in journals, cautiously, over 30 years. Eddington folded his into a manuscript nobody could follow. Schrödinger stood up in a room with a head of state in it and said it out loud, and the mood met the newspapers, and the newspapers do not have a correction mechanism. That is what makes his case useful, rather than merely embarrassing. Nothing went wrong with the physics that had not already gone wrong 4 times. What was different was that this time there was an audience. 11 years later, it happened again, on the radio this time, to a man who had reshaped quantum mechanics at 25, and on that occasion, the correction did not come from Einstein, or from the newspapers, or from an experiment. It came from his own collaborator, in the post, in an envelope, and it was a drawing. The most devastating scientific criticism of the 20th century was a drawing of nothing, sent through the post. To understand it, you need to know the 2 men involved, because they were not rivals. They were close, they had worked together since they were students, and each considered the other one of the few people worth arguing with. Werner Heisenberg invented quantum mechanics. That sentence is an oversimplification, but not by much. In 1925, at 23, recovering from hay fever on the island of Helgoland, he worked out a way of doing atomic physics that discarded the idea of an electron having a definite path and replaced it with arrays of numbers representing what could actually be observed. That became matrix mechanics. 2 years later, at 25, he wrote down the uncertainty principle. He received the Nobel Prize at 31. He also spent the war in Germany leading its nuclear research program, which is a subject with its own enormous literature and its own unresolved arguments, and which is not this story, but which left him a complicated figure afterwards. Wolfgang Pauli was, by common agreement, the most feared critic in physics. He formulated the exclusion principle in 1925, which is the reason matter takes up space, the reason you do not fall through your chair. In 1930, he predicted the existence of the neutrino purely from a bookkeeping discrepancy in radioactive decay, and apologized in writing for postulating a particle that could not be detected. It was detected 26 years later. He was called the conscience of physics, and his criticism was legendary and merciless. He is the source of the phrase that a bad piece of work is not even wrong, meaning it is so vague that reality has no way to disagree with it, which is worse than being mistaken. In 1957 and 1958, these two worked together on what they hoped would be the final theory of matter. It was a single nonlinear equation for a spinor field, one object, one equation, from which all the particles and their masses would emerge as solutions. Heisenberg called it a Weltformel, a world formula. Pauli was, at first, genuinely excited. He wrote to colleagues in early 1958 in enthusiastic terms about what they were doing. For a few weeks, two of the founders of quantum mechanics believed they were closing the book. Then Pauli sat down and worked through it properly. What he found was that the theory did not deliver what was being claimed for it. The mathematics required a particular kind of state space with a strange property, negative probabilities essentially, which have to be removed by hand, and the promised outcome, the derivation of the actual masses of actual particles from the equation, did not happen. There was a framework. There were no numbers. Pauli concluded that the whole thing was, at best, a program, and he withdrew from the collaboration. Heisenberg did not withdraw. He went public. In early 1958, the German press carried the story that the fundamental equation of matter had been found. Heisenberg spoke about the theory on the radio, describing it as essentially complete, with only the technical details remaining to be filled in. On the 1st of March 1958, Pauli took a sheet of paper and drew a rectangle on it, an empty rectangle with nothing inside. Underneath he wrote a caption, and he posted it to the physicist George Gamow. The caption read, "This is to show the world that I can paint like Titian. Only technical details are missing." I want to let that sit, because it is doing several things at once, and all of them are lethal. It concedes the claim exactly as stated. Yes, of course, the picture is finished. In the sense that the frame exists and the canvas has edges. It identifies precisely what is absent, which is everything. And it does so without a single equation, in a form anyone can understand, which means it could not be answered with mathematics. It travelled through the physics community immediately. It is still travelling. 68 years later, it is the first thing most physicists know about Heisenberg's world formula, and for many of them, it is the only thing. Now the part that makes this hard rather than funny. Pauli was ill when he drew it, though he did not yet know how ill. On the 15th of December of that same year, 9.5 months later, he died of pancreatic cancer. He was 58 years old. He had been admitted to a hospital in Zurich, and the room he was given was number 137, the number he had spent his life trying to explain, the fine structure constant's inverse, the same number that had consumed Eddington. He is said to have remarked on it when he saw the door. And there is one more thing in this episode that I think is the most important part of it, and it is easy to skip past. Pauli believed it too. For several weeks in the winter of 1957 and 58, the single most ruthless skeptic in the history of the subject, the man who invented the phrase, "not even wrong," who had made a career out of dismantling other people's enthusiasm before breakfast, was writing to his friends about how they were on the verge of the final theory of matter. He was not being polite. He was caught. That should frighten you slightly. Everyone in this story so far could be explained away individually. Weyl was young, and the quantum era had not arrived. Kaluza was isolated. Einstein had a philosophical commitment he would not let go of. Eddington was 15 years in and could not turn back. Schrödinger was under pressure from a patron and from his own age. You can construct a reason each time. Pauli had none of those. He had no career pressure, no philosophical stake, and an established professional identity built entirely on not being fooled. And for a few weeks the Grail had him as well, and he only got out because he did the arithmetic and the masses did not come. So the last significant act of the conscience of physics was to tell an old friend, in public, that he had painted an empty frame. And he was right, and he had tried to say it privately first, and then he ran out of time. Heisenberg went on working on the nonlinear spinor equation for years afterward. He published on it into the 1960s and 70s. It was never adopted by anybody. It appears in the historical literature, and nowhere else. The man who had rebuilt physics before he was 30 spent his last 2 decades on a unified theory that the field simply declined to take up, and the definitive verdict on it had been delivered by his own collaborator in a letter before the work was even a year old. Two of the four founders of quantum mechanics, in the same decade, spending their final years on this. Schrödinger in Dublin, Heisenberg in Munich, both of them chasing the same thing that had already taken Einstein. But I want to pull out the phrase, because it is going to come back tonight, and when it does, the meaning will have changed. Only technical details are missing. In 1958, that was a joke. It was a devastating exaggeration of one man's overclaim, and everybody who read it understood that no serious person would say such a thing about a fundamental theory, and that was the entire point of the drawing. Hold on to it. We are going to arrive, in about an hour, at a framework that thousands of physicists have worked on for 4 decades, which is regarded as the leading candidate for the final theory, and whose position, stated openly, without embarrassment, by its most distinguished practitioners, is that the structure is correct, and that what remains is the technical problem of determining which of roughly 10 to the 500 solutions describes our universe. That is not a joke. That is the official state of the art. Pauli's rectangle was drawn as satire. It has since become an accurate description of the field's flagship program, and nobody laughs, because at some point along the way the exaggeration quietly caught up with reality and moved in. That is where we are heading. But before we go there, I want to stop and put these 5 men side by side, because we have now watched the same thing happen 5 times, to 5 of the most capable people who have ever done physics, using 5 sets of mathematics with almost nothing in common. And there is something visible in the pattern that none of them could see from inside their own attempt. Let me lay it out. Let me stop the clock for a few minutes and put them all on the table at once, because from inside any single one of these stories, the ending looks like bad luck, and from outside all 6 of them, it does not look like luck at all. Hermann Weyl, 1918, using differential geometry, proposed that the scale of spacetime is locally arbitrary, derived electromagnetism from the freedom, and was refuted by the color of starlight. Theodore Kaluza, 1919, using an extra spatial dimension, wrote general relativity in 5 dimensions, found Maxwell's equations inside it, waited 2 years to publish, and 20 for a salary. Albert Einstein, 1925 to 1955, using classical continuous fields, worked through 4 distinct frameworks over 3 decades, produced nothing the field could use, and died mid-calculation. Arthur Eddington, 1929 to 1944, using number theory, attempted to derive the constants of nature from counting, rebuilt his derivation when the measurements moved, and lost a formidable reputation. Erwin Schrödinger, 1947, using affine geometry, announced a unification at a press conference, watched it dissolve within weeks, and lost a 20-year friendship. Werner Heisenberg, 1958, using a nonlinear spinor field, announced a world formula on the radio, and received a drawing of an empty rectangle from his own collaborator. 6 people, 6 branches of mathematics, with essentially nothing in common: geometry, extra dimensions, classical fields, arithmetic, affine connections, nonlinear quantum equations. If you handed their papers to a modern physicist, without the names attached, they would not obviously be about the same subject. 1 outcome, 6 times. So what is the shared thing? I think there are 3, and they stack. The first is that every one of them tried to unify what was known, rather than what was there. Weyl and Kaluza were unifying 2 forces, in 1918 and 1919, because 2 forces were all anybody knew about. Within 15 years the count was 4, and the 2 new ones were quantum, short-ranged, and completely unlike the 2 they had been working with. Einstein began the same way, and simply continued after the ground moved. Heisenberg was writing a fundamental theory of matter in 1958, and the quark model, the the discovery that protons and neutrons are not fundamental at all, arrived in 1964, 6 years later. Every one of them was attempting a final description of a list that was still being written. And here is the part that has no remedy. There is no way to know, from the inside, whether you are on that list. Nobody in 1919 had a way to find out that 2 more forces existed. The information was not withheld from them. It did not exist. So the instruction, wait until you have all the ingredients, is useless, because the whole difficulty is that you cannot count the ingredients until afterwards. The second shared thing is more diagnostic, and I think it is the real tell. Not one of these 6 theories predicted anything. Go back to Maxwell for a moment, because he is the control case. His unification did not merely rearrange what was known into a tidier form. It said, there exist waves nobody has ever seen, at wavelengths far longer than light, traveling at this exact speed, and if you build the right apparatus you will find them. That is a claim the universe can refuse. 22 years later, Hertz built the apparatus, and the universe complied. Now run down the list of 6. Weyl's theory made a prediction that atoms would differ according to their history, and it was immediately falsified, which is to its credit as physics, even though it killed the idea. After that, nothing. Kaluza's 5-dimensional theory reproduced gravity and electromagnetism, both already known, and said nothing new that could be checked. Einstein's frameworks reproduced gravity and electromagnetism, and said nothing new that could be checked. Eddington's produced a number that had already been measured, and then a different number that had also already been measured. Schrödinger's produced a rearrangement of gravity with extra components. Heisenberg's produced a framework whose promised particle masses never came out of it. 5 of the 6 were, in the strictest sense, not theories about the world at all. They were re-descriptions of the world we already had, written in a more elegant hand. And that is exactly the condition Pauli's empty rectangle diagnoses. The frame is real. The frame is often quite beautiful. There is nothing in it. The third shared thing is the strangest, and I have mentioned it twice, and want to say it plainly now. In almost every case, the mathematics survived. Weyl's gauge principle became the structure of the entire standard model. Kaluza's extra dimension and Klein's compactification became the backbone of string theory. Eddington's affine approach fed into Einstein's and Schrödinger's work. The Grail hunt has been an extraordinarily productive generator of mathematical technique and a complete failure at its stated purpose, and it has been both of those things at the same time for 100 years. Which raises the possibility, and I am only raising it, not settling it, that the value of the search has never been in the destination, and that we have been paying for a road while telling ourselves we were buying a house. Now, everything I have described so far happened before the modern era of physics. No quarks, no standard model, no colliders worth the name, no computers. It would be entirely reasonable to say that these 6 were simply working too early, that they were craftsmen without materials, and that once physics acquired real tools, the picture would change. Physics acquired real tools. In 1974, 2 physicists at Harvard did something none of the 6 had managed. They proposed a unification that made a specific, quantitative, falsifiable prediction about something nobody had ever observed. It was elegant, it was economical, it unified 3 of the 4 forces, and it told experimentalists exactly what to go and look for. They went and looked for it. And what happened next is, I think, the single most important result in this entire story, and it is not a discovery. By 1974, physics finally had what all 6 of those men had lacked, which was a full inventory of the pieces. The 1960s and early 70s had been extraordinary. Murray Gell-Mann and George Zweig had proposed quarks in 1964, and by the early 70s, experiments at Stanford had confirmed that protons contain hard little scattering centers inside them. Quantum chromodynamics had been written down to describe how quarks are bound, and, crucially for our story, something had happened that belongs in the same category as Maxwell, a real unification, proposed, tested, and confirmed. Sheldon Glashow, Stephen Weinberg, and Abdus Salam, working through the 1960s, showed that electromagnetism and the weak nuclear force, which look nothing alike, one being infinite in range and carried by massless photons, the other being confined inside the nucleus and responsible for radioactive decay, are two aspects of a single electroweak interaction. They are different only because a field pervading space breaks the symmetry between them and gives mass to some of the carriers and not others. The theory predicted heavy force-carrying particles, the W and the Z, with specific masses. In 1983, at CERN, both were found at the masses predicted. That is the second confirmed unification in the history of physics, and to this day it is still the second and last one. But notice what it was and what it was not. It was not a Grail project. Glashow, Weinberg and Salam were not trying to write the final theory of everything. They were fixing a specific technical problem with how the weak interaction behaves at high energy, and the unification fell out of the repair. It made a hard prediction, with numbers attached, and the numbers were checked inside 20 years. That is the pattern of a unification that works. Hold it in your hand while I show you the next one. If two of the forces are secretly one, why not three? The obstacle looks obvious at first. The three forces have wildly different strengths. The strong force is, as advertised, strong. The weak force is feeble. Electromagnetism sits between them. Things of different strengths are not the same thing, except that the strengths are not fixed. This is one of the deepest results in modern physics, and it is worth taking slowly. When you probe a particle at higher and higher energies, you are looking at it from closer and closer in, and what you see changes, because the vacuum around any charge is not empty. It seethes with pairs of particles flickering in and out of existence, and those pairs arrange themselves around the charge and screen it. Get closer, and you penetrate more of the screen, and the charge you measure goes up. So the strength of electromagnetism increases at high energy. The strong force does the opposite, and this was the surprise of 1973. David Gross, David Politzer, and Frank Wilczek showed that because the carriers of the strong force carry the charge they respond to, the screening runs backwards. The strong force gets weaker the closer you look. It is called asymptotic freedom, and it won the 2004 Nobel Prize. So you have three numbers that all change with energy, one rising, one falling, one drifting. Plot them. Extend the lines upward, far past any energy we can produce. They very nearly meet. At an energy around 10 to the 16th giga-electron-volts, about 100 trillion times what the Large Hadron Collider reaches, the three curves come together in the same small region of the graph. That near convergence is the single most seductive picture in modern theoretical physics. And if you want to understand why thousands of people have given their lives to this, it is enough to look at that plot. Three forces that appear utterly different, and if you follow them up, they seem to be heading for the same point. It looks like a memory of something that was once one thing. In 1974, Howard Georgi and Sheldon Glashow at Harvard wrote down the theory that made it explicit. They proposed that the strong, weak, and electromagnetic forces are three faces of a single force, described by a mathematical structure called SU5, which contains all three of the Standard Model's symmetries inside it in the smallest possible way. Above that unification energy, there is one force. Below it, the symmetry breaks, and the one force splits into three. The theory was economical, it was elegant, And it did something else that mattered enormously. It put quarks and leptons into the same family. In the Standard Model, quarks and leptons are separate castes. Quarks make protons and neutrons. Leptons include the electron, and nothing ever turns one into the other. In SU5, they sit in the same mathematical multiplet, which means the theory contains new heavy force carriers, called X and Y bosons, that can convert a quark into a lepton. And if a quark inside a proton can turn into a lepton, then the proton is not stable. It can decay, typically into a positron and a neutral pion. The story that gets told about the moment Howard Georgi worked this out is that he realized what it implied, that matter itself is temporary, and found it so bleak that he went and had a drink about it. Whether or not the details are exact, the sentiment is the right one. The theory implied that everything you have ever touched has an expiry date. And it offered something in exchange for that bleakness, which is worth knowing because it made the theory even harder to give up. One of the oldest embarrassments in physics is that the universe contains matter. The Big Bang should have produced matter and antimatter in equal amounts, and equal amounts annihilate completely, leaving a universe of light and nothing else. There is something here instead. You, the room, the planet. So at some point in the first instance, the books did not balance, by about 1 part in a billion. In 1967, Andrei Sakharov had laid out the 3 conditions any explanation would need, and the first of them is that there must exist processes which change the number of protons in the universe. Ordinary physics has no such process. Grand unification supplies one for free. The same quark-to-lepton transitions that make the proton unstable are exactly what you need to explain why there is anything at all. So SU5 did not just unify 3 forces, it promised to explain why matter exists, using the very mechanism that dooms it. That is a hard thing to walk away from. But it also made the whole thing testable, and this is the part I find genuinely thrilling, because the predicted proton lifetime was around 10 to the 31 years, which is a number so large it sounds like a refusal to be tested. The universe is only about 1.4 times 10 to the 10th years old. You cannot wait 10 to the 31 years. You do not have to. You get more protons. Radioactive decay is a statistical process. If a proton has a 1 in 10 to the 31 chance of decaying in a given year, then you do not need to watch 1 proton for that long. You need to watch 10 to the 31 protons for 1 year, and you should see roughly 1 go. And protons are cheap. 10,000 tons of ordinary water contains something on the order of 10 to the 33 protons. At the predicted lifetime, that is on the order of 100 decays a year, several a week. So they built the tanks. The Irvine, Michigan Brookhaven detector went into a salt mine near Cleveland, Ohio, about 600 meters down, filled with roughly 8,000 tons of purified water. The Kamiokande detector went into a zinc mine in the Japanese Alps, under about a kilometer of rock. The rock is not decoration. It is there to absorb cosmic rays, which arrive constantly at the surface and would swamp the signal. A kilometer of mountain cuts the muon flux by a factor of around 100,000. The signal they were looking for is a faint cone of blue light, Cherenkov radiation, produced when a charged particle moves through water faster than light does in water. And to catch it, they lined the walls with thousands of photomultiplier tubes, each one a glass bulb the size of a beach ball, capable of registering a single photon. Come down and stand in it with me for a moment, because it is one of the strangest places human beings have ever built. You are a kilometer inside a mountain. The air is cool and damp and completely still, and it smells faintly of rock and machine oil. You are on a narrow steel walkway, and below you and around you and above you is water, 50,000 tons of it in the largest of these tanks, so pure that it is aggressive, so free of anything to scatter light that you cannot judge how far away the far wall is. Facing inward from every surface are 11,000 glass eyes, in ordered ranks, gold and dark, each one waiting for a single photon. Nothing moves, nothing hums. The whole structure has been built, at enormous expense, and staffed continuously by people who will spend their working lives here in order to watch for one flash of blue light. And the experiment, if the theory is right, succeeds a handful of times a year. Somewhere in that volume, 1 proton out of 10 to the 33, one particle out of a number with 33 zeros after it, quietly stops existing, and 11,000 eyes catch the light it makes on the way out. You are standing inside a machine, built to notice the end of matter. They switched them on in the early 1980s. Nothing happened. Not a slow accumulation of ambiguous events. Not a signal that was hard to interpret. Nothing. The protons did not decay. By 1983, the predicted rate was in trouble, and by the mid-1980s, the minimal SU-5 prediction was excluded outright. The lifetime had to be longer than the theory allowed, which meant the theory was wrong. And then, because this is what physics does, they kept watching. Kamiokande was rebuilt as Super Kamiokande, 50,000 tons of ultra-pure water with more than 11,000 photomultiplier tubes. It has been running since 1996. In 2001, during a refill, one tube imploded, and the shockwave took out roughly 2/3 of the others, in a chain reaction that lasted seconds and cost years. They rebuilt it again. The current lower limit on the proton lifetime in that golden decay channel, proton to positron plus neutral pion, is around 2.4 times 10 to the 34th years. The original prediction was 10 to the 31. The measurement has now pushed past it by more than a factor of 1,000. 40 years of continuous watching. It is very likely the longest-running null result in the history of science. I want to be fair here, because the detectors were not a waste, and the story has a genuinely glorious side. In February of 1987, a star exploded in the Large Magellanic Cloud, and Kamiokande and IMB both caught a handful of neutrinos from it, the first neutrinos ever detected from outside the solar system, arriving hours before the light. That is the founding event of neutrino astronomy. And in 1998, Super Kamiokande demonstrated that neutrinos oscillate between types, which means they have mass, which was the first confirmed crack in the Standard Model, and won the 2015 Nobel Prize. The machines built to catch the Grail caught two entirely different and enormous things instead. But the Grail itself was not caught, and the people whose careers were specifically about grand unification, the model builders, the phenomenologists who calculated decay channels and branching ratios and predicted rates, spent decades producing work whose only measurable outcome was a steadily rising number describing how wrong they had been. Sheldon Glashow, who had a Nobel Prize already for the unification that did work, is reported to have largely lost interest in grand unification once minimal SU-5 was excluded. And here is the thing that changes the shape of the whole story. Grand unification did not die. It retreated. Because SU-5 has larger cousins, supersymmetric versions, and models built on a bigger structure called SO10, and those versions predict longer proton lifetimes, comfortably beyond what any current experiment can reach. They are still viable. They are worked on today. Look carefully at what that means. A theory made a sharp prediction, the prediction failed, and the response was to move to a variant whose prediction lies just past the edge of what can be tested. That is not dishonest, and it is not unusual. It is how theoretical physics normally proceeds. But do it enough times, and you have converted a falsifiable idea into an unfalsifiable one small reasonable step at a time, with nobody ever making a decision they could be blamed for. Remember that phrase. Nothing happened. It is going to keep coming back tonight, and each time it does, it will be attached to something larger and more expensive. The next time, it cost $2 billion, 14 miles of tunnel under Texas, and several thousand careers in a single afternoon. There is a field in Ellis County, Texas, about 30 miles south of Dallas, with nothing much on it. Underneath it, there are 14 miles of finished tunnel, sealed, and in places full of water. It is the most expensive hole ever dug in pursuit of the holy grail of physics, and understanding why it is empty requires understanding the idea that was supposed to be waiting at the bottom of it. The idea is called supersymmetry, and I want to give it a fair hearing, because it is not a fringe notion that got out of hand. It was, for about 30 years, the mainstream expectation of essentially the entire theoretical physics community, and it was believed for reasons that were genuinely good. Particles come in two families. There are fermions, which are the particles matter is made of, electrons, quarks, and which have the property that no two of them can occupy the same state, which is why matter takes up room. And there are bosons, which are the particles forces are made of, photons, gluons, and which are happy to pile up in the same state, which is why you can have a laser beam. The two families behave so differently that they seem like separate kingdoms. Supersymmetry proposes that they are the same kingdom. Every fermion has a boson partner, and every boson has a fermion partner, differing only in that property and in mass. The electron would have a partner called the selectron. Quarks would have squarks. The photon would have a photino. The gluon, a gluino. None of these have ever been seen, which is explained by their being heavy. The symmetry is broken, so the partners are pushed up to masses beyond what we have been able to produce. 3 arguments made this compelling, and the first one is the strongest. There is a problem in the standard model called the hierarchy problem, and it concerns the mass of the Higgs boson. In quantum field theory, a particle's mass is not just its bare value, it receives corrections from every process the particle can participate in, including virtual particles flickering in and out around it. For the Higgs, those corrections are not small. They are proportional to the highest energy scale, where the theory still applies, which, if you take the theory seriously all the way down, is the Planck scale, around 10 to the 19th giga-electronvolts. The corrections are therefore enormous, some 30 orders of magnitude larger than the observed Higgs mass of about 125 giga-electronvolts. For the Higgs to come out as light as it does, the huge positive and huge negative contributions have to cancel each other to something like 30 decimal places. Not approximately, precisely, and for no reason. Physicists find that intolerable, and the word they use for the intolerance is naturalness, the principle that a theory should not require an absurd coincidence to produce the world we see. Supersymmetry fixes it in one stroke. The fermion and boson contributions to those corrections come in with opposite signs. If every particle has a partner of the other type, the monstrous corrections cancel automatically, not by coincidence, but by structure. The Higgs is light because the symmetry protects it. The second argument, remember those 3 force strengths converging near 10 to the 16th giga-electronvolts. In the plain standard model, they come close, but they miss. Add the supersymmetric partners, and the running changes just enough that the 3 lines meet, cleanly, at a point. Grand unification works properly only if supersymmetry is real. The third argument, the lightest supersymmetric partner, would be stable, electrically neutral, and interact only weakly. That is a precise description of what dark matter must be. The theory hands you the dominant form of matter in the universe as a free byproduct. 3 independent problems, 1 solution. And critically, the naturalness argument said where to look. For the cancellation to work without fine-tuning, the partners should sit not far above the electroweak scale, hundreds of giga-electronvolts, perhaps up to a tera-electronvolt, within reach of the next machine. So the field made the next machine. The superconducting supercollider was to be a ring 54 miles around, buried beneath Ellis County, accelerating protons to 20 tera-electron-volts per beam, a collision energy roughly 3 times what the Large Hadron Collider achieves today. It was approved in 1987. Tunneling began in the early 90s. 17 shafts were sunk. 14 miles of tunnel were bored. Magnets were being designed and tested. Thousands of physicists, engineers, technicians, and support staff moved to Texas, bought houses, enrolled their children in local schools. In 1992, Steven Weinberg, one of the architects of the electroweak unification and one of the most respected physicists alive, published a book called Dreams of a Final Theory, making the case that a complete theory of everything was a coherent goal and possibly a near one. He testified before Congress in support of the collider. The book is, in part, advocacy for that machine. In October of 1993, Congress cancelled it. The estimated total cost had climbed past $11 billion. About $2 billion had already been spent. There were charges of mismanagement. There was a new administration. There was no international partner. And the Cold War, which had underwritten the argument that America must lead in fundamental physics, was over. Come and stand on the site with me in the last weeks of that year. It is winter in North Texas, which means grey and wet rather than cold. There is a construction road cut across farmland and mud, and the boring machines have stopped and are standing where they stopped. At the shaft heads, the lights are still on, because nobody has decided who turns them off. Below, the finished tunnel runs away in both directions, smooth-walled, wide enough to drive through, curving very gently along an arc that was going to close into a 54-mile circle and now ends after 14 miles in unexcavated rock. In the site offices, people are packing. The notices went out before Christmas. There are physicists here who moved from 4 continents, who have spent 6 years on beam optics and detector design for a machine that will not exist, and whose specialism, the physics of a 20 tera-electron-volt proton beam, has just ceased to be a career anywhere on Earth. Some of them will go to CERN. A striking number of them will go to Wall Street, where it turns out that people who can model complex systems are worth a great deal of money. Water begins to seep into the completed sections because pumps cost money, and there is no longer any money, and over the following months, the deepest parts fill. The land and the tunnels were eventually sold, more than 15 years later, for a small fraction of what had been spent on them. Some $200 million of infrastructure went for a few million. The buildings have been used, at various points, to store chemicals. The search moved to Europe. The Large Hadron Collider, at CERN, 27 kilometers around, about a third of the SSC's design energy, began colliding beams in 2010. In July of 2012, it found the Higgs boson, with a mass of about 125 giga-electron-volts, essentially where the Standard Model said it would be. It was a genuine triumph and the fulfillment of a 48-year-old prediction. And it was, at the same time, the worst possible news, because the Higgs arrived alone, no selectrons, no squarks, no gluinos, nothing at all beyond the Standard Model. In run after run, at higher and higher energies, in every channel anyone could think of to look in. The current exclusion limits from ATLAS and CMS put gluinos and the lighter squarks above roughly 2.4 tera-electron-volts, the top and bottom squarks above about 1.3, and the electroweak partners above about 1. Every one of those numbers is well past the region where naturalness said they had to be. And this was not one experiment failing to find one thing. The 2 big detectors have between them published hundreds of separate supersymmetry searches, different production channels, different decay chains, different final states, each one a distinct way for the theory to reveal itself, each one designed by people who very much wanted it to. Every single one came back empty. When you have looked in several hundred different places, with the best instrument ever built, and found nothing in any of them, the accumulated silence starts to carry more information than any one search could. Nothing happened. Again, bigger machine, larger collaboration, and the same result as the tanks under the mountain. Now, supersymmetry has not been ruled out, and you will hear that said, and it is true. The framework has enough adjustable parameters that the partners can always be placed a little higher than the current limit. There are perfectly respectable models with superpartners at 10 tera-electron-volts, or 100, or far beyond. But look at what has been given up to keep it. The entire motivation was naturalness, the refusal to accept a 30 decimal place coincidence. If the partners are at 10 tera-electron-volts, the cancellation is no longer automatic. You need fine-tuning again. Less than before, but still absurd. The version of supersymmetry that solved the problem it was invented to solve is gone. What remains is a version that survives by no longer solving it. This is the same maneuver we watched with grand unification, and it is the second time tonight. A theory makes a prediction. The prediction fails. The theory moves to where the prediction cannot yet be checked, and the reason it was believed in the first place is quietly left behind. Nobody lies. Nobody even makes a decision they could be criticized for. Each individual step is defensible. And at the end of the sequence, you have a framework that cannot be wrong, which is not the same thing as a framework that is right. Think about the human shape of those 40 years. A theorist who started a doctorate on supersymmetric model building in 1982, at 24, is now 68. They have written perhaps 150 papers. The mathematics is correct, the calculations are sound, the referees were satisfied every time. And there is no particle. There has never been a particle. The entire body of work describes the properties of objects that, as far as anyone can demonstrate, do not exist. That is thousands of people. It is not a scandal, and none of them did anything wrong, and every step they took was the reasonable step, given what was known. That is exactly what makes it worth looking at. And it is still not the largest example. The largest one is still running. It has absorbed more talent than any theoretical program in history, and its official position, stated plainly by its most distinguished practitioners, is a sentence that Wolfgang Pauli invented as a joke. The largest single act of intellectual commitment in the history of theoretical physics began, more or less, on one evening in August of 1984. The idea itself is old and startlingly simple to state. Suppose the fundamental objects of nature are not points, but tiny loops of something with length, strings, at a scale around 10 to the minus 35 meters. A string can vibrate, and it can vibrate in different patterns, the way a violin string can sound different notes. Each pattern of vibration looks, from far away, like a particle with a particular mass and charge and spin. The electron and the quark and the photon are not different objects. They are different notes. That is elegant, but on its own it would be a curiosity. The thing that made physicists lose their minds is what happens when you list the notes. Among the vibration patterns, unavoidably, there is one that has no mass and carries 2 units of spin. And a massless spin-2 particle is not a free choice. It is mathematically forced to couple to everything in proportion to its energy, which is to say, it is forced to behave exactly like gravity. It is the graviton. Nobody put gravity into string theory. You write down vibrating strings, you work out what the notes are, and gravity is sitting there, whether you wanted it or not. After 60 years of physicists trying to force gravity into a quantum framework by hand, here was a framework that refused to work without it. And the old disease of quantum gravity, the infinities that appear when you calculate what happens at a point where particles interact, go away, because a string has extension, and the interaction is smeared over a small region instead of concentrated at a mathematical point. For a while, it also looked like the theory might be unique. That was the mood of the first superstring revolution, when Michael Green and John Schwartz showed in 1984 that a fatal inconsistency in the theory cancelled exactly, but only for very particular symmetry structures. The constraint seemed so tight that the theory might have no adjustable parameters at all. One theory, one universe, no choices. Physicists moved into the subject in numbers that have no precedent. Within a few years, a large fraction of the theoretical high-energy community worked on strings, and for a long stretch afterwards, the majority of new faculty hires in the field were string theorists, which meant that the alternatives were starved of people as well as money. There was a price on the ticket, and it was one we have already met tonight. String theory does not work in 4 dimensions. It requires 10. 6 of them have to be hidden, and the way they are hidden is Oscar Klein's mechanism from 1926, curled up small at every point of space. Except now, instead of a single circle, you have a 6-dimensional shape. And this is where it comes apart, slowly, over about 20 years. The shape of that curled up 6-dimensional space is not decoration. It determines everything you observe, which particles exist, what masses they have, how strong the forces are. Change the shape, and you change the physics of the universe that sits on top of it. So the question that decides whether string theory explains our world is, which shape? Nothing in the theory answers that. Worse, the number of possible shapes turned out to be not large, but obscene. Once you account for the ways fields can be threaded through the holes in these spaces, the count of stable configurations came out, in work through the early 2000s, at something on the order of 10 to the 500. That is not a number with a physical comparison available. There are roughly 10 to the 80th atoms in the observable universe. Every one of those configurations is a consistent solution of the theory, describing a universe with different particles and different constants. One of them, presumably, is ours. The theory does not say which, and there is no known principle that would. Now hold that against what the Grail was supposed to be. The whole point, from Eddington counting his way to 137, through every attempt in this story, was to explain why the constants have the values they have instead of other values. A framework with 10 to the 500 solutions does not explain why the constants are what they are. It permits them to be almost anything. It is the exact opposite of the thing that was wanted, and it arrived at the end of the most concentrated effort ever mounted to find it. The field split over what to do about that. Leonard Susskind, one of the founders of string theory, argued that we should accept it. The landscape is real. All those universes exist somewhere, and we find ourselves in one with these constants, because the others cannot contain anyone to notice them. That is the anthropic answer, and to a lot of physicists it reads as a surrender, an explanation that explains nothing and cannot be checked. To others, it reads as simply the way the universe turned out, and our discomfort is not evidence. Meanwhile, the theory kept becoming less finished rather than more. In 1995, Edward Witten showed that the 5 distinct superstring theories are limiting cases of a single 11-dimensional framework. He called it M-theory, and pointedly declined to say what the M stood for. That was 31 years ago. No complete formulation of M-theory exists today. We have a name, some limits, and a conviction that something is there. And in 2006, the argument broke into public. Peter Voigt published a book called Not Even Wrong, the title taken directly from Wolfgang Pauli, and Lee Smolin published The Trouble with Physics, and between them, they made the case that the field had spent 2 decades and a generation of its best minds on a framework that had produced no testable prediction and had crowded out the alternatives through hiring and funding rather than through results. Which brings me back to the drawing. In 1958, Pauli mailed his friends an empty rectangle captioned with the line, that only technical details were missing, and it was a joke. A savage exaggeration, funny, precisely because no serious physicist would ever describe a fundamental theory that way. Here is the position of the leading candidate for the final theory of physics in 2026, stated without irony, by people of the highest distinction. The framework is correct. Gravity emerges from it necessarily. The mathematics is consistent. And what remains is the technical problem of identifying which of approximately 10 to the 500 solutions corresponds to the universe we live in. Only technical details are missing. The joke has become the field's official self-description, and nobody is laughing, because there was never a moment when anyone stepped over a line. It happened by increments across 40 years, and every increment was a reasonable response to a genuine difficulty. I want to be scrupulously fair, because string theory is not a fraud, and the people in it are not fools. It has produced serious results. In 1996, Andrew Strominger and Cumrun Vafa counted the microscopic states of a certain kind of black hole and got exactly the entropy that Hawking and Bekenstein had derived thermodynamically 20 years earlier, which is a real and beautiful piece of physics. In 1997, Juan Maldacena proposed a correspondence between a gravitational theory in a curved space and an ordinary quantum field theory living on its boundary, which is the most cited idea to come out of the whole program, and which has been genuinely useful in nuclear physics and in condensed matter. And it has generated mathematics that mathematicians care about independently. There is a catch in the largest of those successes that is almost too on the nose. The Maldacena correspondence works in a space-time with negative curvature, a universe curving inward on itself. Ours has positive curvature. It is accelerating outward. The single most successful product of the search for the final theory of this universe is a precise statement about a different one. And underneath all of it sits a fact that no amount of mathematical progress touches. Strings, if they exist, become directly visible at energies around 10 to the 19th giga-electronvolts. The Large Hadron Collider reaches about 10 to the 4th. That is 15 orders of magnitude, and closing it with anything resembling current accelerator technology would require a machine of roughly galactic proportions. So consider a specific person, someone who finished a doctorate in 1985, at 25, in the wave of brilliant young theorists who moved into strings after Green and Schwartz. They are now approaching 70. They have spent a working life, the whole of it, every good year, on a question they knew from early on could not be settled by any experiment performed while they were alive. They were not reckless. They went where the best ideas and the best people were, which is exactly what you are supposed to do. And they will finish their career without ever learning whether the thing they gave it to is true. That is not being wrong. Being wrong is survivable. Being wrong is how science works. This is something else, and it is the specific injury this problem inflicts. It is spending your one life on a question that will not answer you, in either direction, ever. Which finally brings us to the thing I have been holding back since the beginning. 108 years. 6 brilliant men in the first act, thousands of people in the second, 2 of the 4 founders of quantum mechanics, the most famous scientist who has ever lived, 40 years of watching water, 14 miles of empty tunnel, hundreds of failed searches, and 10 to the 500 solutions where one was wanted. At some point you have to ask whether the reason nobody has found it is that it is not there. So let me stop circling it and answer as plainly as I can. There are 3 serious positions available, and I am going to give each one its due, and then I am going to tell you which one I think the evidence actually points at. The first position is that the problem is simply extremely hard, and we are not finished. On this reading, everything I have described tonight is not a graveyard, but a construction site. Whale-handed gauge invariance forward. Kaluza handed forward hidden dimensions. Grand unification handed forward the running of couplings. The road is real, it is just longer than a human life, and it is unreasonable to expect otherwise when the relevant energies are 15 orders of magnitude beyond any machine we can build. People who hold this view point out that the atom was proposed by Democritus around 400 BC and confirmed by Einstein and Perrin in the early 1900s, a gap of roughly 2,300 years. On that timescale, we have been at this for an afternoon. That is a completely respectable position, and a great many excellent physicists hold it. The second position is bleaker. It says the final theory may be real and simply unreachable, true, correct, and permanently unconfirmable, because the energies required to see it will never be available to anything we can build. If that is the situation, then the final theory is not a scientific object at all. It is a metaphysical one, a statement about the world that is either true or false, and that no observation will ever distinguish. Stephen Hawking, who did more than anyone to popularize the idea that we were close, publicly reversed himself in a lecture in 2002 called Gödel and the End of Physics, arguing that a physical theory is a mathematical model and is therefore subject to the same limits Gödel proved for mathematics, that there are true statements which cannot be reached from within the system. And that is not merely philosophical hand-waving anymore. In 2015, Toby Cubitt, David Perez Garcia, and Michael Wolff published a proof in Nature that a specific, well-posed physical question, whether a quantum material has an energy gap above its ground state, is undecidable in general. There is no algorithm that answers it, and no finite set of axioms from which it follows. It concerns idealized infinite systems rather than a real slab of matter, and it should not be overstated. But it establishes something that used to be a worry and is now a theorem. Undecidability is not confined to pure mathematics. It reaches into physics. The third position is the one I think this history actually supports, and it is the quietest of the three. There may be no bottom. This comes out of the work of Kenneth Wilson in the 1970s, and it won him the Nobel Prize in 1982, and it is arguably the most important idea in modern theoretical physics that the public has never heard of. Wilson's picture is called effective field theory, and it says this: every theory in physics is a description valid over a particular range of scales, and, this is the beautiful part, every theory contains within itself an estimate of where it stops working. Fluid dynamics is exactly right until you get down near the size of a molecule. Chemistry is exactly right until you get down near the nucleus. The Standard Model is spectacularly right up to the energies we can currently reach, and it tells you, from its own structure, that something else takes over higher up. This explains something that ought to be astonishing, and that we take for granted, which is that physics is possible at all. You can design a bridge without knowing anything about quarks. The layers are genuinely insulated from each other. That is why a civilization can make progress in stages instead of having to know everything before it can know anything. And here is the part that matters for tonight. Nothing in Wilson's framework requires the tower to end. Each layer is effective. Each has a layer beneath it. There is no principle anywhere in physics, none, that says the sequence terminates in a final layer that is not effective but fundamental. That is not a result, it is an assumption, and it is so deeply embedded that it does not feel like one. If the tower goes down forever, then the holy grail of physics is a category error. It is like asking for the largest integer, a question with a perfectly good grammatical form and no possible answer, where the failure to find one is not a failure of effort. And even if there is a bottom, there is a second problem that removes most of what people actually want from the Grail. In 1972, the condensed matter physicist Philip Anderson published a short paper called More is Different, and it is one of the most quietly devastating things ever written about reductionism. Anderson's argument was that being able to reduce everything to a few simple laws does not remotely imply being able to start from those laws and reconstruct the universe. At every level of complexity, nuclei to atoms, atoms to chemistry, chemistry to life, life to minds, genuinely new organizing principles appear, which are consistent with the level below, but not derivable from it, in any usable sense. Superconductivity is not in the equation for an electron. It is a property of trillions of them together, and nobody has ever derived it by starting from first principles alone. Which means that even the perfect final equation, handed to you tomorrow, complete and correct, would not tell you how a protein folds, or what a thunderstorm will do, or why you love the people you love. It would tell you what the pieces are, and nothing whatsoever about what they do together. Anderson, incidentally, testified before Congress against the superconducting supercollider. The intellectual case against the Grail and the political case against the machine were made by the same man. So here is my answer, and it is not the satisfying one. Nobody knows whether the Grail exists. And that is exactly the point, because every single person in this story proceeded as though somebody did. Whale assumed it. Kaluza assumed it. Einstein assumed it for 30 years. Eddington assumed it so hard that he rebuilt his own derivation to protect it. Schrödinger announced it. Heisenberg broadcast it. Thousands of supersymmetry theorists and string theorists have organized entire careers around it, and the assumption has never once been demonstrated. It is an inheritance from Maxwell, from one spectacular morning in 1865, when two forces really did turn out to be one thing. In 350 years of physics, there have been exactly two confirmed unifications. Two data points are being carried, as though they were a law of nature, which changes what those pages beside the bed in Princeton actually were. I opened by calling them an unfinished answer, and that is how they are always described, the great man interrupted, the calculation cut off by death. I do not think that is what they were. I think they were an unexamined question, 30 years of increasingly elaborate mathematics resting on a premise that was never once put on the table and looked at, that there is a bottom and that it can be reached, and that reaching it is what a life in physics is for. And I think the most informative result in modern physics is the one nobody counts as a result at all. Nothing happened. Nothing happened in 8,000 tons of water in a salt mine in Ohio, and then in 50,000 tons under a mountain in Japan, for 40 years. Nothing happened in 14 miles of tunnel in Texas. Nothing happened in several hundred separate searches at the largest machine ever built. The universe has been asked the same question, at every scale we can reach, in every channel we can think of, for a century, and it has declined to answer every time. We keep reading that as a delay, it might be the reply, none of which makes the wreckage worthless, and I want to end honestly about that. Whale's discarded idea is the structure of the standard model. Kaluza's hidden dimension is the backbone of string theory. The tanks built to catch a dying proton caught the neutrinos from a supernova and proved that neutrinos have mass. The men who chased the final theory gave us gauge theory, the Higgs mechanism, neutrino astronomy, black hole thermodynamics, and, because Schrödinger got bored in Dublin one February, a nudge that helped start molecular biology. The road is magnificent. It is just that everyone who built it thought they were building it toward a house, and no one has ever seen the house. That is why this idea has ruined more careers than any other in science. Not because it is difficult. Science is full of difficult. Because it is the only problem we have that can accept an entire human life and return absolutely no information about whether you were getting closer. And if you are still awake, here is the thing I would like to leave in the room with you. The assumption those men made is not an exotic one. You make it too, constantly, about almost everything. That underneath the confusion, there is a simple reason, that the layers stop somewhere, that if you dig far enough, you hit floor. It is the most comfortable assumption a mind can hold. Nobody has ever found the floor. Not once. Not in 108 years of looking with everything we have. Thank you for spending this long night with the most expensive question in physics. If taking an idea apart this slowly is how you like to fall asleep, a like or subscribe would mean a great deal. It genuinely helps me keep making these. And remember, the next time someone offers you a simple answer underneath everything, no one has ever shown there is a bottom. Good night, and rest easy.